Uh, Good night, I should say. And tonight, May 30th at 20:52 military time, that is 8:52 p.m., May 30th. I'm here at the Hampton Inn JFK. At the Hampton Inn JFK tonight, and I'm on the topic, the amazing 5x12 matrix discovered by yours truly, and its multidimensional field application. Now, I've been going over this amazing 5x12 matrix now, demonstrating it here in the USA for nearly 3 years now. And so I have, at this time, try to leave out the details, of some little details about this 5x12 amazing matrix, in order to show some relatively more intricate application of this amazing discovery. Once again, my name is Dolphy Gilpin, Dolphy Alexander Gilpin, and tonight I'll be demonstrating some sort of engineering applications to this 5x12 amazing matrix. And particularly, I'll be using this 5x12 matrix to enhance solutions in mesh analysis, circuit analysis problem. And as you can recall, I showed you some 3x3s in the last session over at the Radisson Hotel where I was a couple of weeks ago. Tonight I'm at the Hampton Hill, further down the road. And I'll be doing even a more relatively intricate one. I'm going over to the 4x4 mesh solution, circuit analysis problem. So let me start off here. I'm going to be leaving out a lot of details. And suppose now, my writing pad, oh, here it is. Suppose now we have, say, the general, or the delta, we know was equal to the determinant of R11, R12, R13, R14, R21, R22, R23, R24, R31, R32, R33, and R34, and R41, R42, R43, and R44. We have a 4x4 dual pair matrix here. This is stemming from our 4x4, which was the second step in our PDM processing. And we're seeing now that delta is equal to the determinant of this. Now, as we had mentioned previously, now in previous application, we're just using absolute values of the elements. But now in the circuit analysis, we'll be using the real values, and real values take on the form of plus, minus, plus, minus. That's plus, this is minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. And when we determine these, we just simply take the subscript, and if we add them and if they are even, then it's a positive. If we add them and it's uneven, it's a negative. So 1 and 1 is 2, that's even, that's positive. 2 and 1 is 3, that's uneven, so it's negative. 1 and 3 is 4, it becomes a positive, because 4 is even, and 1 and 4, 4 and 1 is 5, which is uneven, so it becomes a negative. So even take on positive and the odd take on negative. We could also find it by some exponential method there, but we're going to stick to the simpler thing. Or this is not the place and the time to explain those minor details. So we know that delta is equal to the determinant of that. And if we now draw, let's say, a 4x4 mesh, let me see, I draw a 4x4 mesh here. Okay. Let's draw. Just drawing a general 4x4 mesh here with some power. I don't want it to be too difficult here. Alright. There are some powers, power supply, and suppose if I put here, this is 240 volts. This is a positive direction here, clockwise. This is mesh 1. I call it M1. Mesh 2, M2. Mesh 3, M3. And mesh 4, M4. And correspondingly, we see that the current in this direction is I1. This is I2. This is I3. And this is I4. Current going in the clockwise direction, we assume to be positive. If when we make our calculation, we get negative, then we know that the assumed current is in the reverse direction. And suppose now I'm just, that's 240 volts. Suppose this is, say, this is going so from positive to negative, negative to positive. It's going from positive to negative. Suppose that this is 480. And suppose that this is now, I must say 600 volts. And suppose that this is 500 volts. And let's just use some simple elementary resistance. Make our calculation easy. However, we'll have some big numbers in the voltage. 2, 4. Alright, and say that resistance of 1. 3. Now I've drawn a 4-mesh circuit here, and correspondingly we'll have the delta as this, the determinant of this, and we could put in the values of the R11 and the R12 and the R13 from the circuit. Now from inspection, let's put them in. We see now that delta, which is equal to the determinant of now. In mesh 1 here, we add up the resistances now. We get 5 and 5. 0, 5 mean 5. And that's to maintain the duality in the numerics. But I just use 5. Sometimes I would say 0, 5 or 0, 3 is the same thing. To maintain the duality as was presented in our PDM processing. So we added up 5 and 5, 10 and 2, 12. So that will be R1 will be 12. That will be a positive plus 12 there. And R12 is the resistance is in the 1 and 2 mesh now. So this is the second mesh. And the common resistance there will be the 2. And this is negative. And we say no that neutral resistances take on negative. So that will be minus 2. And R13 in the common in the first and the third mesh. There's nothing common in the first and the third mesh here. R1 tree. So that will be 0. And R1 and 4, there's nothing common also in the 1 and 4 in terms of that. This is 4th and this is 1. And so that will be also 0. So we're going to come up with something that makes some simple calculations. And by right, we don't want to keep things simple here, but we'll show you that in real life it won't be this easy. But for the matter of simplicity in our demonstration, we're going to be doing this. All right, so R21, first of all, it will be a negative. The second and the first, and the mutual thing would be a negative, so that will be -2. R22, 2 and 2, M2, mesh 2 here, and that would be now 2 and 4, 6. So that would be 6, positive 6. R23, I take on a negative from our thing. R23, 2 and 3, and there's nothing common in 2 and 3 here, so let's take on 0. And R24, 2 and 4, there's nothing common, so that takes on a 0. R31, 3 and 1, nothing common there, so that's the 0. R3 and 2, 3 and 2, nothing is common here in terms of resistance, so that's also 0. R3 and 3, 1 and 1, 4, that will be 5. And R3 and 4 should be 3 and 4. This is the mutual thing here, which is 4. 3 and 4 is negative, and by right, the mutual resistance take on a negative, so that will be 4 minus. R41, 4 and 1, there's nothing common. R4 and 2, mesh 4 and mesh 2, there's also nothing common there. And R4 and 3, minus 4. And R4 and 4 is 4 and 3, 7. So this is very easy. That will be the determinant of this. A lot of zeros in it, so that would make the problem easy. But like I said, things will not be so easy in real life. But for a demonstration here, we're going to just make it easy. All right, so let's find this then. So delta for this would be 12 into 6, 0, 0, 0, 5, minus 4, 0, minus 4, 7. So you note now that this turns out into the 3 by 3, which you have done calculation on in our previous session. So and this would be now minus 2 into minus 2, 0, 0, 2, 0, 0, 5 minus 4 minus 4, 7. And to be also plus now 0 into something which would make it 0, and another 0 into that. If you further do this, this would be equal now to 12 multiplied by 6 into 5 minus 4 minus 4, 7. this one here plus 0 into 0, 0 minus 4, 7. That should make it 0, and plus 0 into 0, 0, 5 minus 4. So let's just make it now into 72 into 35 minus 16 and these will come out to be 0. So that will be equal now to 72 multiplied by 9 minus 16 and 10 before 9 and 1 from 2 before. 72 multiplied by 19 and that will be equal to delta. Alright, we'll 72 multiplied by 19. Let's do that from our little thing here. 72, 19, 2, 7, 9, 2 is 18, 9, 7, 63, 6 to 4, 8, 6, 13, 1, 3, 6, 8. And here we'll take a break. So we're found delta. We're going to come back now and we're going to find, using Kirchhoff's law, find the numerator value, which is by replacing one column by the voltage, and then we find the currents by taking delta upon the numerator value divided by delta. So let's take a break here and we'll return to find the currents and voltages.